here are for the core. The primary core coil self-inductance, which governs what kind of current. What does it say? XLM equals.
Magnetizing.
I have to increase the size.
Oh, magnetizing current, yeah, magnetizing.
That's a constant, right?
It is. The magnetizing current is a constant value, regardless of the load on the transformer, because they have to produce that magnetic field that's going to transfer the energy, and that's always going to be the same. What changes is the actual other current on top of that, if there's a load. So the primary coil self-inductance governs magnetizing current, or IM. That's what these little sub-M for magnetizing. And then RM is the losses, effective resistance. So you learned about the parts of effective resistance due to AC are more than just DC ohmic. And that's due to the core losses. So the resistance that it would be if you had so many watts of losses in the core. So the core losses are directly related to the XLM and RM, but the core losses, the watts, are RM. So that could be hysteresis, eddy currents, causing vibration and heat, and whatever. Those are the losses in the core. Primary coil resistance deals with, like you have the more current you have I squared, that current squared times that R, of all those terms would be copper losses, be the copper losses. And then they say, what is this little symbol here? XLP. It's the reactance, primary coil reactance loss due to flux leakage. So we hope that all the flux is used and contained inside the core, but if some of that flux doesn't link up or get used, they consider that, quotes, leakage. It's not completely used or linked with, to cause input to output 100%. So maybe you won't get all the volts per turn out of it, or something like that. Okay, and core losses, let's see, secondary coil. So now go to the secondary, XLS and RS. So XLS, there we go, and RS. So the other little inductor symbol is flux leakage in the secondary. So there's some in the primary that doesn't link with the secondary, but they have two. And then RS is secondary coil. That's to do with the resistance of all those windings in the secondary. Which one would have higher losses, do you think? If the primary was the high voltage side, let's say, so that's sort of normal, and the secondary was the low voltage side, which one would have more copper losses from current flow? Main current flow. Which side would have a higher current flow?
Primary high voltage.
No, the opposite. The opposite. The lower the voltage, the higher the current for the same VA, right? So if you think about it now, the low voltage side has bigger wire, lots of amps. You can feed a 600 volt transformer with like little number 8 little baby wire, and then coming out you've got like 4-aught or 250 kc millialuminum or something like that. And you're thinking, why is all this little wire feeds power in? So this is power out. It looks like you're getting more power out. No, you're not. You're getting more current out, but smaller voltage. So VA in equals VA out. So the copper losses will be more on the low voltage side because of the high current and the resistance of the wire, the winding themselves. It's got nothing to do with the voltages. It's got everything to do with the amount of current. Right? Okay, energy losses that occur, core losses and copper losses. So let's see, core losses, we'll do this one. Which side do you connect the voltage to in this case? Low voltage or high voltage?
What are you trying to do?
You're trying to measure core losses.
Would it be high?
High voltage. Well, that's a low voltage side, it says.
Okay, so for core losses, you have to connect the rated voltage to either winding. So usually we have a low voltage available in our building, so they show the low voltage side being connected. So if this was say this was a 600 to 120 volt transformer, right? Just say for example, I have 120 volts available in the building, very easily. So I'm going to use the low voltage side to do my test. You can pick one side, any side, but usually you do that. Then they say carefully isolate the high voltage terminals, so don't connect it to anything. You want it to be open circuited. You don't want any load in the secondary. The high voltage side in this case is the secondary, so it's stepping up. So that voltage is still there, but you're not using it to draw any current. If you did, if you connected any load to this or had anything connected to it, now you wouldn't be measuring just core losses, you'd also be measuring some copper losses. So what you're trying to do is eliminate all the copper losses and only measure what the core losses are. So what current do you have flowing if you don't have anything connected to the secondary?
Zero.
Is it?
The voltage is there.
What current do you have in an inductor? What's that? Magnetizing current. Yeah, magnetizing current. So you got a small little magnetizing current. It's that current that causes what in the core?
Core losses.
Okay, yes,
Current.
but what is it doing in the core? What's the function of the magnetizing current? That little bit of current, milliamps or whatever it is. Half an amp. What's that? Creates heat? Yeah, but what's the purpose? It does create heat, yes. But what's the purpose of having a current flowing through an inductor? Because this is just like an inductor, just to forget about the secondary, right? It's open circuited, it's not doing anything. It's just producing, cutting the conductor with flux. It's producing voltage, but it's not using, just ready to use, right?
Yes.
So what's it doing in the core? Producing magnetic field. Thank you, somebody said. Waiting for that. So the
I
flux.
did.
So the magnetizing current produces the expanding and collapsing flux in the core. That's the purpose of it. It's that energy that gets, it's wattless, but because of the eddy currents and hysteresis and the vibration of the core and all that, those are considered losses in the core as a byproduct of that flux movement. That's sort of a byproduct of moving the flux back and forth across the core. Right? So the core itself has, in a transformer, is going to have some heat. So like remember I said the little doorbell transformer, when you don't push the button, it still stays hot because it's that little magnetizing current is always running in there, even if you're not closing the secondary circuit with your doorbell push button, right? Okay, so they say if you connect this up, measure the voltage to make sure that you have the proper voltage. So if this was a 120 volt primary and a 600 volt secondary, then I'd have to make sure I'm measuring the rated voltage. So apply the rated voltage to that winding. Then remove the voltmeter because you might get some voltmeter loading from this. You don't want the wattmeter to read any of the losses that might be in your voltmeter. You pull it out of there once you're sure that the voltage is right, pull it out of there, so that's why it's a dotted line. You want to know what the current is here so that you can, I don't know if you really need the ammeter in this case. All you're going to read is the magnetizing current anyways. Okay, so what you're going to read is the core losses. That makes sense? No load on the secondary, it's just whatever the core is doing to create the magnetic field and then the losses because of that. Next one. You got to short circuit this puppy. So let's not use the rated voltage. If we use the rated voltage on the winding and short circuit the secondary, it's going to be, it could be a big explosion, you might see smoke. So what you have to do is use the high voltage side, let's say the 600 volt side, flip that guy around, and do not use the rated voltage. Short circuit this, watch that ammeter to whatever, let's say it's this one. This one is 500 VA. So on the 600 volt winding, 600 volt winding. Let's make this one, since I have it here, 600 volts. And this is short circuited, and this is 120 volts. 500 VA. So the watt meter, in this case, is going to read the losses when it's at rated current. So as long as I have the rated current, through that winding, remember that it doesn't matter about the voltages, it matters about the amount of current for the copper losses, because you'll have that current squared times the resistance, whatever the resistance is of those windings. So whatever that is. So what is 500 VA divided by 600 volts for current?
0.83.
Very, very small. So 0.83 amps?
Yeah.
Okay. So you measure, you turn up that voltage, and whatever that voltage is, let's say that voltage ends up being 2 volts. I don't know, it's pretty low. Okay, let's go 10. Let's go 10 volts. Let's say it took 10 volts, that variable supply, to reach rated current. You're not producing a huge VA here. You're not producing a lot of problem with short circuiting this. When you short circuit this, when this primary is drawing rated current, the secondary will also be drawing rated current, because this is the load. That is a resistive load, almost 0 ohms. It's like 0.01 ohms or something, right? So it's considered negligible resistance, but it is a resistive load. That's a huge load. A short circuit, 0 ohms would be the biggest load, right? It's inversely proportional. So 120 volts, what would be the rated current of this second winding? 500 VA divided by 120.
1.17.
Sorry?
4.17.
Okay. So you got 4.17 amps flowing in there, but you don't have to measure that. You know that if this one is measuring rated current, that one is also measuring rated current. You can clamp it. You can clamp it and check. Ah, yeah, I got 4 amps. Right? Is that going to hurt it?
No.
No. You go right up to rated value. At full load, you're going to measure the maximum copper losses on your watt meter, because you're having rated current, I squared times R on the winding. That would not be the core losses at all. And the reason for that is the flux, the counter EMF is actually canceled off once load starts being drawn through the winding. So we're going to get to that in the next learning task, why that is. But what you have is you've got your main voltage, your source, and then you've got your counter EMF. And what happens as you build up load on the transformer is that this gets less and less and less, the counter EMF. That's why it allows more current to flow. So we'll get to that in the next learning test. You'll see why that is. But so really by doing that, because the counter EMF is less, it's almost like you've canceled out some of the reactance out of that coil. So it actually sort of negates all the core losses that you were measuring with the magnetizing current. So the magnetizing current is almost canceled out. It's because it's so small anyways, right? And that's what they say here. So it's in your book as well. It says, okay, negligible core losses. So they say that doing this test is negligible core losses because the core losses are such a small percent of the total losses, and because the rated current is in the circuit, it reads the full load copper losses. So what they say, and you gotta just believe it, core losses plus copper losses is our total power loss in the transformer. But you gotta do the rated values. So the core loss, use the low voltage side, powered up to rated voltage, take the watt meter reading, but make sure the secondary is open. The copper losses, you gotta short circuit the secondary, but you can't use the rated voltage, otherwise you're gonna have smoke, right? Where there's smoke, there's fire. So use a very small voltage. This voltage that you measure is called the impedance voltage. So when you make that test with the voltmeter, take it out. Once you get it there, take it out. So I've reached 10 volts, I've got 0.83 amps, I'm turning up my supply, maybe I have it at one of the benches, turning up my supply, 0.83, okay, good, stop. What's the voltage? I got bang on 10 volts. I don't know, it could be anything, right? 7 volts, 12 volts. I got bang on. That would be your impedance voltage. The percent impedance of the transformer is that voltage divided by the voltage that it should have been on that winding. So 10 volts out of 600 volts is what percent? What was it as a decimal?
0.016.
0.016?
16666.
Okay. So that would be 16, 1.67.
The answer is 0.0166.
Yeah, so it'd be 1.6% impedance. Using the copper loss test, you can figure out the percent impedance of the transformer and also figure out the copper losses at the same time. You can do two things with that test. So what two things does the copper loss test do?
Shows you the copper loss and the impedance.
Yeah, so and what test is that? What's the test called?
And short circuit.
Short circuit test. Yeah. What's the other one called for the core losses? Open circuit test. Yeah. Alex?
So, you like have your variable voltage, with the knob per se, whatever it is. Turn that to your the rated current, and whatever that voltage is divided by your, what the coil is rated for.
That's right. Yeah.
Okay.
Yeah. And the reason for that is, I'm trying to simplify it. The reason for that in the book this percent impedance. The percent impedance, we'll get to the watt losses in a second because that's an easy calculation, but this one is sort of a new thought. The percent impedance is the percent of rated load impedance that the transformer has. So whatever load impedance that transformer would put on it would cause a limiting factor to the grid, you know, a certain grid. It doesn't allow a complete million amp short circuit or infinity amp short circuit. It's going to be somewhere around maybe 70,000 amps or 50,000 amps or 10,000 amps or somewhere in that range. It'll limit it. And what's limiting it? The impedance of the transformer. So they say, okay, what's the percent impedance of that transformer when it's at rated full load, of the full load that you would connect to it? And so the available fault currents, you can calculate the fault current with that, and you can determine whether you can parallel or like parallel two transformers. What it means is they draw current. If two transformers have the same percent impedance, they draw current in the same way. Whereas if one had a higher impedance, it would draw less from that one and more from the other one, right? So the higher the impedance in a transformer, if they're the same, they'll draw equally from both.
Which is important when you're paralleling them.
Oh yeah. Percent Z or percent IZ. So if I said, okay, this voltage here, right, instead of IR, right, the IZ drop, this would be the IZ drop across the winding. Once I'm supplying 10 volts, I also have a 10 volt drop, right? So for every source supply voltage, you have, for every voltage rise, you have a voltage drop, right? So the voltage drop, if I had this voltmeter here measuring, I'd have a 10 volt drop across that winding. Is it purely resistive?
Yeah.
No.
Ah, shit.
So the 10-volt drop would be IZ, not IR,
Right.
right? IZ drop. So that IZ over the total rated voltage, which is 600, would be IZ times I rated. Now the short circuit times the Z of the transformer, and the rated times the rated load. So if this would be, if you short circuited the transformer and used that short circuit voltage or that impedance voltage divided by the rated voltage, if both currents are the same, the short circuit current in this case and the rated current are the same, they cancel each other out. So you're left with Z of the transformer, or the impedance of the transformer, divided by the impedance of the rated load. And that's a percentage. So there you go. So mathematically, the currents cancel, so you're left with Z over Z, what I'm saying. So it's a percentage of Z. It's actually a percentage of voltage, since the currents would be the same in this test, the short circuit current in this case, then it works out. Like,
You're saying the currents are the same, but one's 0.833 and one's 4.17.
What's on the other side?
not anymore.
That makes a little more sense.
If that's muddying the waters here, then leave that out. But you know that whatever this current is short-circuiting on the secondary, it's also like a short-circuiting, not short-circuiting, it's a shorted transformer winding. It's the maximum that this can carry, because it's shorting the leads.
So the whole transformer has 0.833 amps running through it?
The primary has.
Primary, yeah.
Just,
The secondary has.
Think of the
one.
ratio, right?
Yeah, but it's a lower voltage.
You have a ratio, so it's different.
Same VA.
okay.
Yeah, same VA in this case. Okay. So how do we calculate short circuit current?
Full load.
Impedance voltage by the, VA, I don't know. That's-
Percentage of the,
What you do is you take the, if you use this formula, that's percent Z, right? I got the percent Z. Say this transformer is 1.67% impedance, or percent Z, correct? We calculated that. How did we calculate that, Mo? How did we calculate the percent impedance when we did this test? What two voltages do we use?
it's VA divided by, no,
No.
V divided by VA.
Impedance
V divided by V? We took the test voltage.
Yeah, divided by.
So. The test voltage became the impedance voltage in this test. 10 out of 600. So we got 1.67% of that voltage. So the percent impedance, if the transformer was at full load, would be 1.67% of whatever the connected load is what it's saying. Because this load was 0 ohms. Okay, so now we can take this transformer, this formula, and take I short circuit over I rated times, and is this not Z transformer over Z rated the same as percent Z? Isn't that what they told us here?
Yes.
Yeah, okay, times percent Z. Hang on a sec,
And you rated that?
hang on a sec.
Time 100%.
Yeah, equals, not times.
What?
Something like that.
percentage.
No, it's not, that's not what it is. Hang on a second. Yeah, it is. So what you have is you take this from all that, and you get this formula right here. Let's just put it in a nutshell. You get the short circuit current available at the terminals of the secondary windings, because you want to know what it's short circuiting at the secondary windings, is going to be, I don't know, for some reason it's not working out. Anyway, forget that.
No, it's right.
It's not. just looked at the map. It's I rated divided by percent Z.
Yeah, that makes sense.
Yeah. So that's your formula. So if you take this current rating, what is the rating of the secondary? So now we can use secondary,
4.16.
right? You take that, that's the rating of the secondary, because usually you care about what you're doing on the secondary, you don't really care about what's going on the primary, right, Kyle? Usually the secondary, because you're connecting everything up to that. And then you go I rated, which is 4.16.
So when we talk about rated current, you're actually talking about the rated current of the secondary.
Yes.
Okay, great, that helps.
So how many amps will be available as fault current if those things were short circuited together and we had all the regular voltages?
This is an insanely high number, really big.
249.99999.
Okay,
251.
260.
249?
That's 251s.
I get 260.
You're drunk, Harold.
I'm drunk.
Okay, boys, we gotta get our decimal markets.
You boys back from the dead.
250.9.
250.96.
Yeah, he used his exact decimals, yeah.
251 amps, how's that? Okay, so we have a potential of 251 amps short circuiting on the secondary of this transformer. Yeah, on the secondary.
That's not what we want.
That's a lot.
It seems a bit high, doesn't it?
That's short circuit current, so that's fine. So this has a certain percent impedance, we calculated at 1.67%.
Yeah.
So it's 1.67% of whatever load can be connected to it. If you short circuit the terminals, if I power this up with 600 volts, and I should put a little wire across there, short circuit, I'm gonna have 250 amps being drawn on the secondary.
Would that like blow up?
It'd be bad. It'd be bad.
Okay,
So
thank
your
God, it's
fusing,
Yeah,
has to be able to handle the short circuit current.
Yeah, but in
You're
this
winding?
one's, yeah, okay, yeah, I understand.
Your fusing, even though you have 1 amp fuse, it has to have an interrupting capacity of, let's say, at least 300 amps. Usually it's 5,000 amps for every breaker, 10,000 amps for a fuse, right? It's an interrupting capacity.
So, the whole thing I'm getting here is that we shouldn't be shorting out the secondary, because that seems like way too high. The windings of secondary should be able to handle that many amps. It's
You
great.
don't want to, you're right. So that's the whole point.
Okay, I thought we were just trying to do this.
You're not applying 600 volts here, you're only applying 10.
Right, okay, so this
So
is
it's all-
this is what happens when
You're
you
getting
apply-
rated load, and from that rated load, you're figuring out the percent impedance. That
Yeah.
percent, and also the copper losses.
Okay.
And so the percent impedance will determine what the short circuit current would be if you short circuited that thing when it was running normally. There you go.
Clarity.
This is just a test to find what the short circuit would be, so
Yes.
you know what fuse to put in.
So you know what how strong that fuse has to be able to handle the energy
Yeah.
that it will, when it's a short circuit condition. So it
Rather
doesn't
than
blow up.
going, well, that didn't work.
Yeah, you don't want the fuse to blow up. I've got pictures of blown up fuses. You know, that you don't want to use a fuse that has less of an interrupting capacity than, like, if it's, say you have 20,000 amps you calculated here. Let's say a bigger transformer had 20,000 amps.
Short circuit.
And you use a breaker that's rated for 10,000 amps.
Yeah, it's not.
What's gonna happen to that breaker?
It's gonna melt.
It's not gonna be able to contain the energy when it tries to open it up, and it's gonna blow up in the panel. So that means you gotta get one of the larger frame breakers that are rated for 50,000 amps. So we're gonna get into H3 after transformer protective devices, and it has everything to do with the short circuit conditions,
Gotcha.
right? Okay, so I'm trying to make this actually practical. It's,
Yeah.
and at the
That
same
wasn't-
time, some people are
Before you
overthinking it. It's
practical.
really not that.
I thought this was a conversation based on like what we're trying to accomplish.
Actually, yes.
Oh, fuck.
Remember this. Remember that formula.
Okay.
That's the one you want to remember for your
Is-
transformer calculations.
So rated, same as full load, as it says here.
Full load amps. Yeah, what it's rated for.
Okay.
Full load is just, yeah, you don't wanna go
That whole
above
message
40,
just
right?
like got.
Yeah, here it is. Okay, what's the available fault current at a secondary terminal of a step-down transformer rated for this?
About
You're going for gold.
Yeah, I think we're lost.
You just need
We're not there yet.
100 kVA.
What do you want to short circuit?
What?
Okay, so let's try it.
I know.
I feel like I just ran a marathon that was like really.
He's drawing it out though.
Okay, and they say the percent said is 3%. 3% Z. You could just put 3% Z.
Holy shit, 27,777
Yes.
Yeah.
amps,
So if I had things running, you know, motors,
30,000.
whatever, and then in the junction box,
27.
something happened here. I've now short-circuited the whole kit and caboodle set. And so we have the short circuit current running through the secondary of that transformer. So what is it rated for normally? 100,000 divided by 120.
833.
It's,
8 tree? Okay.
Yeah. It's hard to say, it's to make fun of some.
Okay. Divide that by 0.03. What do you get for fault current if I short-circuited that down here by accident?
27,777.7777 amps.
almost.
So like 30,000 amps.
What are they doing?
So I need a heavier duty breaker than just a regular breaker. How many parts here to show you? But,
How'd you get the 27?
You
Again?
go, you gotta find your secondary current.
You take this
100,000
number,
100 kVA.
divide that by 0.03, just like that
Okay.
formula says, and you get that.
All right.
So, yes?
Isn't it going to be 0.003?
No. They said 3%. Okay.
Yeah.
Because you're used to all this, like, you might prepare shit. It's tripping.
Okay, let's go back. That's very important. Remember anything, remember that formula. It's pretty easy. Unity power factor, what does that mean?
Unity power factor?
Yeah.
It's like 100?
100%. Okay,
Is that the?
so we did the, here's, in this example, we did a core loss test.
What's the unity for the function?
What test was that?
For me,
What test did they use for the core losses?
the open circuit.
Open circuit test. Okay. And then they said in the question here, and they said that that was 1,200 watts. Right? It had full load copper losses. What test did they use for that one? Copper losses?
That's the,
Short circuit.
Short circuit test, 'cause you need current, so you got a short circuit, okay? Short circuit test, gave me how many watts? How many does it say there? Full load copper losses?
Watt?
What?
Stay on page, guys. 1627, okay. If the secondary is delivering full rated 250 kVA at unity power factor, so what they're saying is the transformer in this example 1 here has a short circuit, or not a short circuit, it has a full load connected to it, drawing full load, 250 kVA. So if it's 250 kVA at 100% power factor, how many watts is that?
Same number.
250 kilowatts.
Yeah,
Yeah. Yeah, if you're 100% power factor, there's no bars.
it's just like resonance.
Right. Okay, so that's the key ingredient on that one. So, but one thing you could say is that if cosine theta is 1, right? Then you could say that the VA times the cosine of the phase angle will always work in this formula. So if you know the power factor, or the VA times the power factor, that's what this is, ES, IS, cosine theta, is the VA of the secondary times the power factor of the load. If you have the total power factor of the plant, or the building running at 100%, well then
Said
it's
it weird.
cosine of theta is just 1, it's 100%. That's the power factor. So we said 250,000 VA times 1, and they call it watts.
Would it not theoretically be 0 cosine of mu?
The phase angle is 0,
Yeah.
right? But the
Oh,
cosine
It'd
of
be
the phase
1.
angle is 1. That's the power factor.
I guess so.
You're correct. 0 phase angle. Okay, so that's why they threw in the 250,000 watts. So what is the efficiency? Well, they added it all up. They said, okay, where did they get the 1200 go?
This is core losses.
Where did the 1562 come from?
That's gotta be the copper
Primary
losses.
coil and secondary.
Secondary.
Secondary copper losses?
Okay, they combine them. So full load copper losses is 1627 plus 1562. Okay, I don't like how they separate it because you're not going to get
Separate core loss.
separate in their test. You're going to get the sum of those in your copper loss test. You're going to get all the copper losses, primary and secondary.
Cool.
31.99.
So the only way they could have achieved that is if they took the watt meter in secondary and took a watt meter in primary and then subtracted to figure out what the primary was only all by itself. You know, I don't see the point. So those are the total copper losses. You add all those up, you add them to 250,000 watts, depending on the power factor of the circuit. And what was the power out? The same 250,000 watts minus the losses, right? And then you get 98.3%. Well, you should anyway. What do you think of that?
That's just fine.
Yeah. So all these are the losses. So you're going to get a question on your quiz, and it'll tell you what the core losses are this, the copper losses are that. Just put them in the power in column, right? It's all what went in before it was lost.
It's always
CJ, power in is power out plus the, yeah, you're CJ. You're Kyle.
Nice neck shorts, dude.
so all your losses will be on the denominator, or
Secondary with that, that's worth it.
So forward
Yeah,
is always.
yeah, plus the watts themselves.
yeah, okay.
If there were 0 losses,
Core and it's always copper losses.
what is the efficiency?
1?
10%, yeah.
Super was you.
Mike? Core is always copper losses plus core losses, right?
Never seen that.
Okay, here's an interesting one.
Two brothers that
What?
Yes.
Just one question. So the power then always copper losses plus core losses, right?
Yeah.
That's
you
for
gotta-
power then.
Yes, you add those in, yes. Add it to the watt, you have all the watts. Like the total watts out, you have to add those to those watts out to say what went in.
What? What?
Okay, so
Draw a schematic.
what about this one? Two transformers are parallel together. What are the ratings on them? 2400 slash 4800, 130 slash 240. What does that mean? Michael, what does that mean to have the two voltages listed on the primary and two voltages
You
listed on
have
the
a
secondary?
two options. Multi-coil, is that what it's called?
Yeah, multiple, so two options for voltage connection.
Lowest one is the coil.
Nice.
That's it.
Whoa.
Hey, John, you saved the class. They're really getting bored of me.
Okay, I'll try to wake them up. Hey!
Hey.
You're not the only board class that we tell you automotive guys this morning.
Mm.
Yeah. Just,
Uh,
Yes.
Yeah, they like that all the time.
not a good sign.